So, hi everyone, my name is Philipp. I recently finished my bachelor at the Ludwigs-Maximilian University in Munich. I'm working as a security and backend engineer at the company Best Bytes currently, and I plan to do my master here in Amsterdam at the UEA. So I did a bit of research on network intrusion detection in the last 2 years, and especially with the use of machine learning for that purpose. I do a lot of programming, mainly Go, but also other languages as needed. So I'm also interested in hardware security, not only software security, and I do a bit of reverse engineering as a hobby. So just to give you an overview of what my talk is about today. So first of all, I want to make clear what kind of problems I try to solve here, and you're gonna get a brief overview of the NetCap framework, what it can do for you, and I'm gonna give you a brief wrap up on what I did in my experiments. And then finally, I'm going to introduce some of the new features I've implemented for the Hack in the Box. So let's start by talking about the really big problem for the software industry currently, and that is memory safety. There was a talk from Matt Miller, who's an engineer at Microsoft security team, and they published some really interesting internal statistics they had about how many of the fixes they pushed out as Windows updates were addressing problems with memory corruption. And almost 70% of the vulnerabilities were related to memory corruption. And that is a pretty strong number, I think. It's just a huge attack vector. And, well, we have to work on getting rid of this. And it's not only for Windows, of course, it affects basically every major platform. And if you're interested in this, there's a really nice Twitter feed I stumbled upon. It's called Fish in a Barrel. And they do basically exactly that. They monitor updates for all kind of big softwares. And then they point out how many of the fixes that were included in the update were related to memory corruption. And if you look at this, it's really frightening. So like, and it affects every major platform. Like in this case, 22 out of 23 in macOS Mojave update, 8 out of 10 in Safari update, 27 out of 31 in iOS. So basically, this goes for all kind of major platforms, no matter if Android, major browsers, whatever. So, and so what we're doing currently is like we're using mitigations, but as the name mitigation implies, it's not addressing the root cause. It's just making it harder to exploit. And you might wonder, how does this memory safety topic affect network security monitoring? Because we have to parse a lot of complex protocols, and most of the time these frameworks are implemented in low-level languages such as C or C++. And as you know, things can go wrong, especially if we parse untrusted input. And so let's have a brief look, just looking up some well-known intrusion detection systems and throwing them into the CVE database. And for example, for those vulnerabilities we get for Bro, half of them is related to memory corruption problems. And for Suricata, we find also a lot of memory issues. And even more, if we look at for example, the release logs, so a lot of these issues don't get CVE numbers assigned, so the dark digit is probably much higher. And also in the recent Suricata update, it was published like 1.5 weeks ago, and it contained like 4 out of the 10 fixes were addressing memory corruption problems. And if we dig a little bit deeper and look at their commit history, we will find even more that's not mentioned in the release logs. And yeah, most of the things are just memory corruption problems while parsing network data. So let's have a brief look at the mitigations in current intrusion detection solutions. So Suricata is using Rust for several parsers. They started using Rust for the DNS parser, and by now there are certain other protocols also using Rust for parsing. But if you look at the ratio from C code to Rust code, well, the majority is still C. So to be precise here, it's 340,000 lines of C to 17,000 lines of Rust. So still is a long way to go. What's nice, although, is that for the next version of Suricata, they make Rust mandatory. So before that, currently it is still optional. And this way they don't have to have separate implementations. Bro, for example, now they renamed to Zeek, which is a pity because I really like the name Bro. So they are using a parser generator to address these issues. This is probably the most simple illustration of a parser generator you will ever see. And basically, it's just reading a format specification and generating C++ code for parsing the format that you expect. But yeah, this is supposed to be safe, but well, there have been problems as well. And so in the generated code generation in general is hard, and it's even harder to generate good parsing code. So yeah, also there have been numerous problems with memory corruptions for the bin pack. So another major problem is our dependency on signature-based detection methods. Because as you know, a signature is made to detect a known thread. And if you're being attacked with something new, then it's not known. So, well, machine learning is quite a nice idea to fix and to address these problems. And the idea is basically you train an algorithm to know what is normal in your network, and then you let it report on things that are new or suspicious. And yeah, like Kaspersky Lab is talking about 330,000 new unique malware samples they get every day. And if each one of those gets a new signature, your database with signatures is growing exponentially, I would say. So, and of course, we can obfuscate existing malware to make it undetectable again. So, we need to find a way of dealing with these issues without being dependent on signatures. And yeah, I think we have a problem here, and we need to address this. And so to fix the first issue with the memory safety, the most obvious thing here would be just using a language for the implementation that provides memory safety. In my opinion, there are two good candidates for this currently. There's like Go and Rust. In my case, I chose Go because I like the language. It has a garbage collected runtime, and it has not yet been successfully attacked, which is quite interesting. So you can also throw Golang in the CVE database and check for results. And all the bugs that are listed there currently are logic errors. And no memory corruption attacks against the runtime. So NetCap stands for network capture, and basically decodes network packets and generates audit records from those. I'm using the Go packet library for decoding the packets. It's well maintained. It's owned by Google. NetCap has a concurrent design. It's using a worker pool. That's a very common pattern for Go applications. And the audit records that you get, I output them as protocol buffers. Wait, protocol buffers. This weird RPC format from Google. Why am I using this? So it's really nice for this purpose because it gives you type-safe structured data. And protocols are not always flat, and they do not always only consist out of scalar values. So we needed a way to present that and to represent complex nested structures. And the other nice effect here is that protocol buffers are platform neutral. So it works a bit similar to the parser generator, but it's more of a type definition generator. So you can basically write protocol definitions, buffer definitions, and then you can generate the type code for the language you want to use them in, and you can use them as type-safe structured data, which is really powerful. So just a brief overview what NetCap does. Basically, we're fetching packets from an input source. It could be live from a network interface, could be from a dump file. And then these packets are equally distributed to a pool of workers with the round-robin strategy, so nothing special here. And each worker basically dissects all the layers and writes all the audit records in the corresponding files, and also filters out traffic that we cannot decode or that had errors when decoding. Workers are buffered, so each worker has like an input queue, and you can configure the size of the queue. So it's I try to keep it as configurable as possible, so you can really tweak it and look what works best on your system and where you get the best performance out. So let's talk a bit about the audit records that you can get. I'm dividing here between two things. So one are the layer types, and one are the custom audit records. The custom audit records, currently I have a flow model, which is just a unidirectional connection. Then the connection type offers the same field as the flow, but it's just bidirectional. And there's, for example, also an audit record type for TLS handshakes that also includes the JAR3 hash and like all the cipher suits that have been negotiated in the handshake, for example. And then there's an audit record type for HTTP, which is a special case because an HTTP request or an HTTP response can be split up upon multiple network packets. So that's why it's not included in the Go packet library by default. And we need to do TCP stream reassembly to basically parse the HTTP requests. So these are the layer types. So these are protocol-specific audit records. And as you can see, I just highlighted the most important ones. But yeah, all the basic protocols are supported from TCP, UDP, IPv6, DHCP, DNS, ARP. And since version 039, there are a couple of more. One which is might be interesting is the USB protocol. I'll get to that in a second. So what does an audit record look like? An audit record has a timestamp when it was observed, and then it has several fields. And the field could also be a substructure, for example. And then I'm writing all audit records of a certain type into one single file. And each file contains a header that has some meta information, like, for example, what was the source where we got those audit records from, where was it captured from, at what time was it captured, and of course, what type of audit records are in the file. So the file then gets the extension .ncap for netcap audit records or .ncap.gz if it's compressed. This is just a simple example for a flow or connection audit record. And on the left, you can see the field names. And on the right side, I've populated them with some dummy data. So protocol buffers are a message-based protocol. So they're not made to be written to disk by default. So we have to implement a little trick for that. So, and the most common approach here is just to prefix each serialized message with its own length. So we can write that to disk and parse it back quite easily. And you just encode the length as a variant and then you can write it to disk. So netcap, I call it the data pipe here, because basically if once a layer type or once you have a decoded protocol, it's being passed in the data pipe. And this is basically a thread safe mechanism for writing those to disk, and you can write into it from several threads. It's synchronized, and then the audit record will be serialized, delimited, compressed, buffered, and finally written to disk. So in order to make it easy to work with the records, I have a mechanism for exporting them, for example, as CSV. So you can select certain fields and you can select the order of the fields you want to have. And by the way, this is a mistake. It should be net.dump. I didn't update the slide as I just noticed. But yeah, anyway, so you have a lot of command line tools and you can use it to operate on those audit records files. Then there's functionality for creating labeled data sets, because for my experiments, I was using a supervised machine learning strategy. And I needed a way to label my audit records. And I implemented that quick and easy with using Suricata. So basically, I'm generating audit records from an input PCAP file. Then I'm using Suricata to obtain alerts for the PCAP file. And then I'm mapping those alerts back onto my audit records and generate that as CSV. So also, you can use it in a distributed setup. So with like a central collection server and agents that are exporting data, and you can collect them. And these audit records are being sent as batched UDP datagrams, and they're also encrypted in transit. So quick use cases. Well, I think it's quite interesting for now for monitoring honeypots, maybe for forensic analysis as well, and of course for research. That's why I created it in the first place. It's open source. So now just a very quick wrap up what I did in my thesis. Basically, I picked a very recent data set from the Canadian Institute for Cybersecurity. I spent a lot of time looking at different data sets. Please don't use NSLKDD anymore. It's totally outdated. The Canadian Institute for Cybersecurity, they have really, really good data sets that are well documented and up to date, and also for different scenarios on Tor, non-Tor, VPN, non-VPN. So there are really a lot of good stuff. I chose the intrusion detection dataset from 2017. It's really well documented. It's around 50 gigabyte of original PCAPs. That's important because many universities, for example, they strip their datasets. They remove IP addresses, hardware addresses, whatever. And I wanted the full data dump, basically, to work with that. So it's 5 days of traffic. Monday is the normal day. Tuesday is brute force attacks. Wednesday DOS. Thursday web attacks. And Friday a bit of botnet traffic. So key takeaways for me from the experiments: before we pass the data to the neural network, we need to encode it. And because the neural network can only work with numeric data. And the strategy you choose for encoding the data has a really big impact on the performance. So for example, at first I tried encoding alphanumeric values with the dummy variable approach, and this basically inserts a new column for each unique string that you have in your data set, so your data set grows in width, and that was a bad idea. So another interesting observation is that I got a really high detection accuracy with just a handful of extracted features. So extracted or generated features are those that we have to compute. So it costs resources to generate them. And the other ones were collected features that are directly available, like port numbers in a packet header, for example. So I was only using a handful of features like kind of durations for flows or connection, or the payload size for certain audit record types, and the payload entropy in some cases. So another interesting takeaway was for me that we can increase the value of the alerts for the analyst by using different strategies for the labeling. So think of using the attack classes as label. We could also use the concrete attack name as label. So in that case, the alert would not say, okay, it's a web application attack, but it would be more precise. Okay, it's a cross-site scripting or whatever. And yeah, the last thing is the accuracy for the protocol-specific approach. So for just looking at the audit records for certain protocol types was really high on average. So that was quite interesting for me as well. And it performed better in a lot of cases than the flow or connection models, for example. Yeah, so development on NetCap has not stopped since I released it in December 2018. An interesting thing to note is that I was able to improve the serialization performance for the protocol buffers just by exchanging the code generator that generates the code for packing and unpacking the protocol buffers. And this was a super easy performance gain, and marshalling them is now twice as fast, and unmarshalling also got a big speed up from that. So that was a really easy fix. And I'm now using it's called the GoGo code generator for the protocol buffers. It's really nice. Also, it's now possible to capture packet payloads. That wasn't intended in the first place, but since we already got it offered by GoPacket, I made it optional, and you can now use a flag to capture the payloads as well and preserve it for some audit records, for example, like TCP, UDP. Then it's also possible to decode USB traffic now. So this audit record type is also offered by GoPacket, which got me curious, of course. And if you install Wireshark, you can bring up a special interface, and you can also attach to it and then decode the USB traffic live, which might be interesting for some kind of applications. And it's also possible to capture the payloads for the USB audit record type. The CSV output that you can generate from the audit records is highly configurable. You can choose a custom separator symbol, and you can now also configure the way that I flatten substructures when putting them into the CSV. So, for example, we have a message with certain fields, and then you can choose what should be the delimiting symbols around the structure and what should be the internal delimiter. And you can configure the way substructures appear in the generated CSV output. I restructured the command line interface. So there are now 8 standalone command line tools. One for capturing, one for working with audit record dump files and exporting them to CSV, for example. So that's the dump tool. Then there's a tool for doing the labeling I've just talked about. There's a tool for starting the collection server. There's a tool for the sensor agent that is exporting data. Then there's a new tool, it's called net.proxy. It's basically a simple HTTP reverse proxy, and I'll go into a bit more detail in a second. There's a general util, and there's a tool for exporting Prometheus metrics, which is also new. I did a bit of improvements on the library side, so now you also have a writer type. Previously, you only had a structure for reading audit records back, and now you have also a writer that basically implements the data pipe I've just been talking about. And also I made the Go packet decode options configurable, so you can have a bit more options to play with. Apart from that, I decided to pre-generate the type definitions for a few common languages and include them in each release. So you don't have to do this yourself. You can just download the latest release, and if you want to work with the data then in Rust or Java or whatever, you can just use the pre-generated ones without having to set up the proto-compiler. There's no Python support, and what's interesting here probably is that you can read it directly into a pandas data frame, which might be interesting for some kind of machine learning applications. So since it's a really common library used there. I published this in a separate repository on my GitHub. It's called PyNetCap. So yeah, let's talk about the proxy. So Netcap currently has a small problem, and that is Go packet implements TCP stream reassembly, but only for TCP packets that are transported over IPv4 currently. So efficiently, this means Netcap is going to miss all HTTP traffic that's being sent over IPv6, and that's bad. So in order to tackle that problem until there is a working IPv6 stream reassembly implementation available, I just decided to use a simple reverse proxy setup. So you can either spawn one or multiple reverse proxies, put them in front of your web applications or web services, and then you're just going to extract HTTP audit records. And the nice thing here is that while doing it this way, I can use the tracing functionality for the HTTP from the Go HTTP standard library. And I can give you a couple of more interesting fields here. So for example, the total time it took from request to response, the time it took to resolve the DNS query, the time it took until we received the first byte of the response, which might be interesting for some timing attacks, and also the time it took for the TLS handshake to complete. Metrics. So I've instrumented the application, and you get three types of metrics currently. One are Netcap internal metrics. So it's about what kind of protocols did we see, how many decoding errors have been there, stuff like that. Then we have metrics for the Go runtime. This is just the standard Prometheus Go exporter, and it gives you some interesting insights about memory usage, the number of Go routines that are currently running and stuff like that. And also, this is the most interesting part, there are now metrics for the audit records, which means we can visualize the audit records. And this is quite interesting because it's very abstract machine data, and I wanted to have a way to visually see and look at my data set and basically try to understand it this way as well. And so the way this works is quite simple. So you have the net.export command line application. You can attach it either to the network interface and do it live, or read a PCAP file, or you can export audit records files that you previously captured. And you just expose at a certain port. You have a handler for that exports metrics, and you configure a Prometheus daemon to scrape that one, and then you configure a Grafana to scrape the Prometheus, and then you can visualize it in Grafana. And I'm currently working on building a nice dashboard for this. This is just a quick preview. I'm going to release it probably somewhere in the next week. So you can see the number of audit records that have been generated, what kind of audit records, and the total number of packets, how many unknown protocols were in there, how many decoding errors were in there, and stuff like that. This is just the overview page. And I started also building one for HTTP. So basically now you can do it for every kind of audit record that's being offered by Netcap. You can start building metrics for it, and and visualizing those. And so yeah, we're just looking at the distribution of user agents, what kind of hosts have been dialed up, how many times, and stuff like that. So yeah, and this is the one for TCP. Is quite interesting. You can also see this is like the payload size over time, and this one shows the payload entropy over time. And yeah, so this way we can get a bit of a better understanding on what kind of data we operate on and what's in there. And yeah, so to help you get started quickly, I've also created an Alpine Linux Docker container that can just pull the container, run it, and all the tools are pre-installed in there, so you can just start hacking. There's now a simple website that gives just a brief overview of the project, so it's easier to find. And the major new change is now there's finally a real documentation available. So for a long time there was only my thesis, and it was quite extensive, but I knew that people wanted a proper documentation. So now you have one. I use the Git book for that. It's quite nice, and it's responsive. You can use it on your phone or whatever. And I try to make it easy to get started and to understand what you can do. So let's talk a bit about future plans. One of the next things I'm going to do is implement support for using Jara rules for labeling. So I think that would be kind of interesting, because for my first experiments, I didn't have a huge JaraDB rule base, but I think some do. So for them, I think it might be interesting. I'm going to do a bit of benchmarking in the next iteration or working on the project, just to get an impression on how well it performs compared to a C implementation. And I've also been thinking about building like a deep packet inspection module that you could use to run certain pattern matches or analysis on the payloads before they are being discarded. Because for a lot of protocols, currently I cannot set the application protocol type because we just don't know it. But this way you could implement it yourself and start doing this. IPv6 stream reassembly for TCP would be really, really interesting. And yeah, and also like a generic interface for application layer decoders that require stream reassembly, because there are more protocols that rely on this. And so it would be really nice to have a generic interface for like a decoder that just gets as input the stream of all the decoded data, and then he can work on this and create the audit records that you actually want to extract. That's it for now. If you have any questions, yes, please. And otherwise, yeah, just contact me by mail or whatever. So, Simone.
Yeah, so thank you. So, thank you, Philipp. So, if there are any questions from the audience, let's start from maybe here. You have a microphone.
Thank you for the presentation, first of all. And question is, can you just briefly talk about the deep learning model that you use for the 95 to 99 accuracy, and on how many data samples did you got those numbers? Yeah, that slide.
Okay, so the experiments were operating on the dump file for each day. So I don't have the exact number of audit records that were generated for this, but it's roughly 10 gigabytes of traffic that were observed for each day. And basically, I have the thesis here as well. If you want to take a look inside, I have a printed version with me. So I have all the tables with all the values from the experiments. So maybe that will answer the question better.
Yeah, but I was curious about the model itself that gave that performance. It's like, is it a fully connected neural network, a random forest? What is it?
Yeah, so I just used Keras, and the model type was sequential.
Okay, so just
5 layers,
connected, 5 layers.
ADEM optimizer.
Oh, that's cool.
Nothing really fancy here, you know. It's like, yeah.
Thank you.
Thank you, Rob.
Okay, so next question over there. Yeah.
Thank you. Oh, it's loud. My question was actually a follow-up to this one. So can we download your thesis to go further into this? Because that 95 to 99% really triggered me.
That's great. So the thesis is available in the root of the repository.
Okay.
So it's on GitHub. It's also on ResearchGate. Please have a look.
Excellent. Thank you.
Cool.
Yeah. By the way, the slides of this presentation will be available on the website, and you can freely download them, of course. Any other question? We have still time for one, probably.
Hi, thank you. Oh, it's on. Okay. Thank you for the presentation. It seems like a really lot of work that you put into this project. Are you currently the only one?
Yeah, it's a one-man project. So it's a bit of an evolution of my tool chain that I've built over the years. So I've been working a lot with the Go packet, and I tried to unify it in a way that also others could use it, and that also like it was better suited from the use case I wanted to work with it. So yeah, currently it's a one-man project, but contributions are welcome. So if you're interested in hacking on this, please contact me. I have a lot of ideas for new features, but very little time. You know how it goes. So yeah, let's see where this is going.
Kudos.
Okay, so thank you very much, Philipp, for your answers. And yeah.
Cool.